Okay, so let's talk about number 8. This is modular arithmetic 1. So we have some instructions to reduce some things modulo other things. The first one is mod 7. Um, so the first thing I'm going to do is I'm going to replace 152 with something that is equivalent modulo 7. So how do I find things that are equivalent modulo 7? What I'm allowed to do is I'm allowed to add or subtract any multiple of 7 that I want. So because I don't like thinking too hard, let me say the following. I'm thinking of a multiple of 7 that is approximately this. I'm thinking of 140. That's a nice round number that's a multiple of 7. So 140 is a multiple of 7, so I can just subtract that, so I can write 12 to the 143. In fact, I really wasn't thinking too hard. Maybe I should have thought of 147 instead of 140. But in any case, now that I'm down to 12, I can subtract 7 again to get 5 to the 143. I could also subtract 7 again and say that this is negative 2 to the 143rd power. That's probably not too helpful, maybe a little bit helpful. You might try it and see what happens. But I'm not done yet. 5 to the 143 power is still a huge number, and I have to figure that out, or at least I have to reduce it modulo 7. I would suggest now repeated squaring. So all of these congruences will be mod 7, so maybe I'll stop writing mod 7. For the rest of part A, everything is mod 7. So 5 to the 1 is just 5. 5 squared would be 25, which is the same as 4, because if I can subtract 21. And then this is repeated squaring. So if I square that, I'm going to get 5 to the 4th. So 5 to the 4th would be 16, which is 2 modulo 7. If I square that, I'm going to get 5 to the 8th. So that would be 4. And now it looks like I see a pattern, because if I square that, I'm going to get 5 to the 16th. But I already had a 4. When I squared that, I get just 16 again. And I know that 16, this is the same as 2. So basically this goes 4, 2, 4, 2 from here on out. So 5 to the 32 would be the same as 4. 5 to the 64 would be the same as 2. 5 to the 128 would be the same as 4 again. And now I'm going to stop because, well, if I went one farther, this would be like 5 to the 256th, which would be a larger power than what I need. I only need 5 to the 143rd. So how do I get 5 to the 143rd? I should be able to make it out of these powers that I have. First, I'll take 5 to the 128. And yeah, what is 143 minus 128? I guess it's 15, isn't it? Yeah. So I still need 5 to the 15th. So 5 to the 16th would be too big, so I won't do 5 to the 16th. I'll do 5 to the 8th. And let's see. I needed 5 to the 15th, so now I still need 5 to the 7th. So I'll do 5 to the 4th, 5 squared, and 5 to the 1. That should work, right? 128 plus 8 is 136, plus 4 is 5 to the 1/40th, plus 2 plus 1 would be 143. Yeah, so this 5 to the 128th was 4, 5 to the 8th was also 4, 5 to the 4th was 2, 5 squared was 4, 5 to the 1 is just 5. And now, yeah, these numbers are still too big for me. I mean, keep in mind that I'm very lazy, so maybe I just took these two 4s and made a 16. I took these and made an 8, and I left the 5. And I'm doing that just so I can reduce as I go, because I don't want to even think about what 16 times 8 is. I mean, it's not even that big of a number, but I don't have to deal with big numbers, not even that big. 16 is the same as 2. 8 is the same as 1. So rather than dealing with 16 times 8, I would much rather deal with 2 times 1. So at this point I can see that this is 10, which finally is congruent to 3 mod 7. So that's the answer for part A. For part B, actually, part B is the secretly easy one. Because if I take this, and the first thing I would like to do is replace the 13 and the 7 with something that's reduced modulo 6. But see, 13 is the same as 1 mod 6, because I can subtract 12. I can subtract any multiple of 6. So 7 is also 1 mod 6. And so this is 1, this is 1. So we're done right there. Because I mean, this was so easy because we got 1s. Now let me grab another piece of paper and do 8C. Where is my paper? Okay. Okay, so the first thing I would do once again is reduce 13 and 7. Unfortunately, they're not going to be 1. Because modulo 5, 13 is the same as 3 and 7 is the same as 2. So, well, okay. There's one way to do it with repeated squaring. There's let's see. Yeah, so maybe I'll try to get creative on this one. I could do this one the same way I did part A. Like, I'll just find powers of 3. I'll do like 3 squared, 3 to the 4th, 3 to the 8th by repeated squaring. And then I can do powers of 2 separately. And then once I figure out what 3 to the 50th is and what 2 to the 40th is, then I can multiply those. So that's a way to do it. There's another way to do it with Fermat's last theorem. And there's also maybe, so this is getting a little bit creative, because what I'm doing is, well, 3 times 2 is 6, which is 1 mod 5, and I really like that. Of course, I have to be careful because the power of 3 and the power of 2 aren't the same, but what I could do is this. So it's like I'm combining the 3 with the 2 as much as possible. Like I've got 3 to the 40th and 2 to the 40th here. Of course, originally I had 3 to the 50th, so I have some leftover 3s. But this is a neat way to, because now this is 6. 6 is the same as 1 mod 5. So basically I get to ignore this. It's just 1. So now let's just deal with 3 to the 10th. So we've made some good progress. Regarding 3 to the 10th, that's still kind of a big number, actually. I could do repeated squaring for that. Maybe let me show you Fermat's last theorem. Or, sorry, Fermat's little theorem. Yeah, not the last theorem, but whatever it is, whatever you call it. Right. For Fermat's little theorem, you have a prime, and this is going to work because 5 is prime. This wouldn't work if we weren't dealing with a prime, so keep that in mind. But if A is not 0 mod P, then A to the P minus 1 is 1 mod P. So 3 to the 4th would be 1 mod 5, because 5 is prime, 3 is not congruent to 0 mod 5, so then 3 to the P minus 1, which is 4, that should be 1. So 3 to the 10th, well, that's 3 to the 4th times 3 to the 4th times 3 squared, which is 1 times 9, which is 9, which is congruent to 4 mod 5. So there we go. I encourage you to try this one the other way, like try this one using repeated squaring or something else. There's multiple ways of doing this one. I wanted to show you a little bit of a different way because we did part A by repeated squaring, so I figured I would show you something else here. Repeated squaring is probably the most applicable method because repeated squaring works whether you're doing modulo a prime or not. Fermat's little theorem only works if you're doing modulo a prime, but repeated squaring always works. So that's, if you're going to learn one method, that's probably the safest method to learn. Okay, so yeah, I'll call this good.